Thanks so much, Donna, for sharing your vision for QMIT and for your deep commitment to bending the trajectory of quantum towards impact. Thanks also to Ian Waits, to Anantha Chandrakasan, and to Nurgis Mavalvala for championing this new initiative. So QMIT has grown out of decades of MIT leadership in quantum science and engineering. And it's impossible to pinpoint one single defining moment in its history. A helpful reference point is the summer of 1981, when MIT hosted the first Physics of Computation conference. It gathered nearly 50 top researchers in physics and computing to explore the promise of quantum for computation, and amounted to essentially the unofficial kickoff to enabling quantum applications. Over the next 45 years, MIT researchers have broken record after record in pushing the capabilities of quantum materials, sensing, computing, algorithms, and communication, working across all 5 schools, the college, and as Dana mentioned, Lincoln Laboratory. Many of you right here in this room have made seminal contributions that brought us to this moment, a new initiative that spans the Institute. There isn't a more important technological field right now than quantum, with its enormous potential for impact on both fundamental research and practical problems. And we built QMIT on a foundation of problem-driven missions, which are designed to thrive in shared intellectual spaces and ultimately in shared physical space. QMIT will help us to ask the right questions, identify the most critical problems, and create a roadmap for developing quantum solutions that are both transformative and accessible. Because even as we continue to navigate a challenging landscape for higher education, the world continues to look to MIT for the ability to invent future technology. Now, I'm thrilled that you all are here with us today as we set out together to invent the future of quantum. And I'm especially delighted to introduce 2 quantum pioneers who will kick off our program, Jay Gambetta and Hartmut Nevin. Both are dedicated to moving quantum beyond theoretical concepts to practical, large-scale applications. And we've invited them here today to share their unique insights on the best way to get there. So just a very few brief words of introduction. Jay Gambetta is the Director of Research at IBM and an IBM Fellow. He oversees global strategy and initiatives in quantum computing, AI, hybrid cloud, and semiconductors. He previously served as the Vice President of IBM Quantum and was named an IBM Fellow in 2018 for his work to advance superconducting quantum computing technologies and to shape MIT's strategy to bring quantum computing to the world. Under his leadership, IBM launched the first cloud-based quantum platform, developed QuizKit, an open-source quantum software stack, and built partnerships with more than 300 organizations. Hartmut Nevin is the founder and lead of Google Quantum AI and the Vice President of Engineering at Google. In 2007, he implemented the first image recognition algorithms on a quantum computer. In 2019, his team demonstrated that a quantum computer could solve computational problems that were intractable for classical machines. More recently, in 2024, the quantum AI team solved a 30-year challenge by implementing successful quantum error correction with their Willow chip. These short sketches only begin to convey what Jay and Hartmut have accomplished. So now we'll let them speak for themselves, first individually and then in conversation with another quantum pioneer who is well known to us at MIT, Ike Chuang. Now, I know you're eager to hear from all of them, so let's get started. Jay first. Thank you.
Thank you. So it's my pleasure to be here and give you a quick overview of IBM. Given that it's 15 minutes, I'm going to skip all the things we're done and focus on 2 messages. I want to convince you that we, as a community, can build a fault-tolerant quantum computer by the end of this decade, and then we need to start thinking about how we are going to scale it beyond. So it is our goal at IBM by 2029 to develop what we're calling IBM Starling. It will be 200 logical qubits running 100 million operations. Okay, rather than just state it, I want to show you why we're so confident this can be done. But before I go there, I think we need to remind ourselves, and I'll go quickly through this, what it means to build a fault-tolerant quantum computer. In some sense, these are like the fault-tolerant equivalent of the DiVincenzo criteria, but I think of them more as guiding. So first, we have to actually have a fault-tolerant architecture. That's one. Everyone will agree that every logical qubit needs to be addressable. And second, everyone will agree that we need a universal set of operations so we can do everything that is possible in quantum computing. What we're pushing is we also want this code or this architecture to be adaptive so that I can make measurements, do my error correction, correct future operations, and allow I can continue to do this. We also want it modular. I don't want to build a code or an architecture that is beyond the tools we have today. I want to build a quantum computer within the CMOS technology we have today, so I want a modular code. And then thirdly, I don't want to waste qubits. I really want the codes to be efficient. And I want to make sure that we're getting the most out of every qubit we put on the chip. So in about 2019 at IBM, we stopped investigating what is known as the surface code. And we actually went on a quest to hire many students. So for all the students in there doing error correction, and actually many of them came from MIT, we wanted a code that could be efficient. And we went to and investigated this code that we called LDPC, well, a version of an LDPC code. So in 2024, we showed how we do a memory. Rightly so, the community would critique, that's just a memory. So then in this year, we showed that you could do a full set of operations and still be efficient and put out an architecture. Then for these more advanced codes, if you want this adaptive nature I talked about, then you would criticize that the algorithm to decode them is too complex to run in the timescales that are needed. So how do you actually come up with a decoder algorithm that can be both efficient? And we showed that it's possible to do a real-time decoding algorithm we call relay belief propagation rather than the more advanced codes. So think of this as the blueprint. Putting all this together, and I don't have time to go into it, we came up with a complete framework where we can have logical memories, logical processing units, universal adapters, all connected together in this modular architecture. I will point out that Ted Yoder is a graduate of MIT, Andrew Cross is a graduate of MIT, and you can clearly see their contributions to creating this architecture as we go forward. So this memory is kind of a donut. So you would say superconducting qubits have never gone to the level to go beyond nearest neighbor corrections. So if I need to make a donut or this sort of donut architecture in commercial CMOS fab, how am I actually going to do it? And so what this video shows is I want this donut, and as you saw at the start of the video, to realize this, you have to break it into multiple different planes, each one of these planes connecting qubits over longer distances and still make it work. So what this means is you really have to invest in packaging. You have to have the ability to do bump bonds through silicon vias, as well as multi-level wiring. And this is exactly what we've done at IBM. We've got technology that allows our qubits to sit on a different wafer, our readout to be on another wafer, and our I/O to go in and out on a different wafer. So we've basically separated all the parts of the qubits. This is still not enough to break the plane and get quantum buses. So what we've done over the years is we've invested on three different things, which I show down the bottom. First is, how can we connect qubits over very long distances? Okay, so I showed I need this donut. I need to be connecting them over a long distance. So here I show that we can connect qubits in a few millimeters up to 14 millimeters and not see any degrading of the quantum gates. Then what I show in the middle is now we need to go up across a plane, back down, and have a quantum gate that allows them to be connected. And so we have to make a quantum multi-level wiring using a dielectric that doesn't lead to any loss, and this can be done as well. So now I can connect them up, come back down. Then if I want to do error correction, I need the ability to reset qubits really fast, and we've shown that we can reset qubits with 3 parts in 10 to the negative 5 in about 10 nanoseconds, which is enough to get really good entropy out of the system. All of this means we have to go to commercial fab, we have to go to automated EDA. All of this is in place so we can design these complicated things. To show this is not fiction, we've already designed one of these error correction chips. You look at the one on the left, this is our leading processors that if you've used any of our quantum computers, Heron is our current leading one. Compared to the one on the right, you can actually see the technology is now gone and looks more like the CMOS technology of the past. And if you look at this, you can see the multi-level packaging all through it that allows this connectivity to get done. So more than this is you have to keep pushing towards system size. I want to get across that this is not just physics, it's systems. We've come up with ideas where we can design very large cryogenic objects so we can cool down and get all of our quantum computers working. Here just shows how we where we intend to disaggregate the fridges and connect all the pieces together. You need more density inside the actual fridges so you can connect more qubits inside a single fridge. Our goal is to get up to about 3,000 per cryogenic environment. And this means we have to go from traditional coax cables all the way to superconducting connections. You need to go to, if you want to build one of these systems and not require many nuclear power plants to control it, you have to go to cold CMOS to be able to control the qubits. We've already demonstrated that we can control these using 50 times less power with our CMOS architecture. And then finally, you need a decoder. So you need to be able to decode, as I said. We came up with the algorithm, but how are we going to implement it? And this is exactly what we've done using AMD FPGAs. We need to actually decode this in a few nanoseconds. So I hope I show you that all these pieces are together, that it's possible to build this fault-tolerant quantum computer. Now I want to switch and say, well, is error correction done? I actually believe very much to all the students, no. There's so much to do in error correction. As you see, we switched from the traditional code to an LTPC code and given you an architecture. But as I think further, I want to remind everyone that concatenated codes and this idea between inner and outer codes, and I think there's a great example by Google themselves where they looked at this yoke code, but there's so much more that can be done as we go to these sort of concatenated codes that you can really start to ask the question, how do you explore algorithms and error correction that matter for the algorithm that you want to do? As an example, you can start to think of, can I use algebraic codes on top of LTPC codes to get better performance and things like this? So for all the students doing error correction out there, I would say error correction is one of the most important things to continue looking at. As an example, we can also start to show we can mix post-selection. So people would say, well, you need fully fault tolerance, which I totally agree to get the base. But on the outer, you can actually start to say, can I sample in time and do space-time checks and use quantum information with post-selection to push it to the ultimate limit? As two examples, we can use post-selected error detection codes to really demonstrate really large logical qubits. The best we've done is 140 logical qubits, creating GHZ states that have twice the improvement over the decoded one. And then if you want to do even look at a really complicated graph states, for the experts in the field, these are states that are driven by Cliffords, you can actually see ridiculous improvements by doing these space-time post-selected codes. So I would say as we go forward, you can do all this error correction on top of these inner codes and create an architecture for the future. So I hope I convinced you that there is a path, and sorry, it's very fast, I only had 15 minutes, to get towards building a fault-tolerant quantum computer, and that there's so much to do. But we also want to go beyond just building a fault-tolerant quantum computer. We want to ask how we changing compute fundamentally. And I've got two examples to say in there. I'm a big believer that the future of computing is CPUs, GPUs, and QPUs all working together. I think a CPUs is very good at doing addition, GPUs is very good at doing tensors, and QPUs is very good at doing circuits. I love this quote by Feynman that says, Feynman Dyson, that says, scientific revolutions are more often driven by new tools than new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have yet to be explained. And so exactly on that, and I'm not a chemist, and I agree that the chemists will improve this. In chemistry, a chemistry problem is related to how well can I get the accuracy of some type of rate by estimating different energy levels. And because if I make a mistake in estimating this, and that rate is exponentially dependent on it, it basically becomes very, very hard to estimate these rates. And so quantum computing, one of the reasons we're so excited about it is not only simulating the quantum computer, is we can get accurate results out of them doing things like phase estimation long term. But we can ask ourselves, can we look at near-term applications by using the quantum as a subroutine of the classical computer? And with many of our partners, this is exactly what we've done. We've looked at, can we actually inject the quantum computer as a way to create an input into a classical algorithm where the rest of the steps are done with the classical algorithm? Riken looked at iron-sulfur molecules, Cleveland Clinic looked at super interactions, Lockheed looked at methane-type molecules, and Boeing have looked at different types of applications that are interesting for them. And if you put these all together, what you see is we're starting to get this layout where it's not only how much quantum computing you're using, it's how much classical computing you're using. And you're seeing this, this experience of mixing and putting quantum and classical together is allowing you to do these very interesting problems and get to larger things. So my first point is we need to reinvent how algorithms are done, using quantum and classical together, and can we use quantum as a subroutine into the classical algorithm? The second is, we also have this envision that why just limit quantum computers by themselves? Why can't we start to connect quantum computers to other quantum computers and make distributed networks? Can we connect quantum computers to eventually sensors, or can we connect different quantum computers together? And exactly what we've started to do at IBM is we've developed this thing we call a quantum networking unit, which allows to take our best processors we have today, connect them to a tunable device that can then be connected to eventually an external field. And so if I just put some of these together, and I didn't have enough time to go in how we intend to scale those modules for the error correction, we're working on this thing we call the L coupler that allows us to connect multiple of the modules together. But if I want to go further, and I want to be able to have distinct cryogenic environments connected, say, by a microwave chamber, which I can switch on and off, say at 4 Kelvin, then how do we connect a quantum microwave photon to a waveguide at 4K? This is a project we started with Fermi. Another one is eventually you want to connect these quantum computers to optics. How do we actually connect a quantum computer to eventually something in the field we call a transduction unit to be able to connect basically a microwave photon to an optical photon and then connect further. And this is a project we started with Caltech and QNext at Argonne. And then ultimately, I would also want to be able to connect a microwave photon to a flying microwave photon so I can start to inject systems in there. And so I think there's this whole area emerging of bringing quantum computers and quantum communication together that I would like to see more of. So on that, I don't think we should just be thinking just about building a fault-tolerant quantum computer. How are we building the architecture of the future that brings all of these together? And that is my 15 minutes, very fast.
Good morning. So I would like to add the perspective from Google Quantum AI. As you can see on the slide, our mission is to build quantum computing for otherwise unsolvable problems. And how are we planning to do this? A number of years ago, we published a roadmap that has 6 steps to take us to 1 million physical qubit machine, which would translate to about 1,000 or a few thousand well-protected logical qubits. And we are about at the halfway point of this roadmap, where was mentioned earlier, the first milestone of this roadmap was to show for the first time that there is a mathematical benchmark problem that can be done quickly on a quantum processor, but would have taken many, many years on a classical machine. And then in 2023, we did, for the first time, demonstrate that quantum error correction actually works in practice, making good on a 30-year challenge. And now we are in front of what we call milestone 3, is one well-protected logical qubit with an error rate of 1 in a million. Our overall roadmap has, of course, a hardware track, a software track, and importantly, access to places like QMIT or QMIT accessing Google's quantum processors. So let me start with the hardware update. I mentioned the 23 result, but it was a little bit anticlimactic. Yes, we did quantum error correction, and the logical error rate came down, but just by a hair, 4%. So people were not terribly impressed. So we did it again in 24, and here you can see it worked much better. Every time we increased the code distance, the logical error rate came down by a factor of 2. And also it passed by a physical qubit. So this was really showing, okay, this works in practice. Might be worth mentioning that this experiment created billions and billions of dollars in value because many quantum startups were in danger of being delisted after this experiment. Woof. That was something for the students to keep in mind. Then we did another experiment that gained a little less attention, but I find extremely encouraging. A qubit is a two-dimensional object, so you have to protect 2 degrees of freedom. But if you focus just on one of those two, you can go to larger code distances. And we did this. And then you can see that we could drive down the logical error rate to 10 to the minus 10. So you could do a pretty complex algorithm with such a low error rate. So in some ways, all, quote unquote, we have to do now is go from this 1D experiment back to a 2D experiment. But it's very encouraging. It seems to work. Then here quickly showing the specs of our processor. Probably too much information to digest this slide. What I would like to say, at Google, we emphasize overall system engineering. There are groups that have more qubits, there are groups that have longer coherence times, but ultimately everything has to fit together well. And we emphasize these system-level experiments that show how well the overall computer works as a computer. And since the Willow announcement last year, we haven't stood still. So our chips now, that experiment was done with 105 qubits, but we now went to 500 qubits. We also had nice improvements by T1. So the Google group traditionally didn't have the very best coherence time. So in 22, we had about 20 microseconds. But then you see every year, if you look at the 50% mark there, it got better and better and better. And now we can routinely do over 300 microsecond coherence. So this is nice to see. So the logical error rates at a rather small d equals 5 code is already approaching 10 to the minus 4. And there's one very important factor. I mentioned it already. We call it lambda, the error suppression factor. Again, in 23, it was barely above 1. Then in 24, we got it to 2. And now we are approaching 4. So that is quite encouraging. Other people, Jay showed this already, of course, no different. Here we need to have better, larger, ideally modular cryostats. And then the piece that probably gives us the biggest headache, actually in the previous slide, you could see these beautiful chandelier pictures. They actually show, in a way, an engineering abomination, which is that every coupler, every qubit needs its own wire. It's hard to build a 1 million qubit system out of this. So one of the things we're working on is better wiring. And was mentioned earlier, Google acquired MIT spinout, Atlantic Quantum, and they hopefully help us with the cryogenic control electronics that will get rid of this engineering problem. So here, this is a slide I'd like to show to our CFO when asking for the next installment of our budget. It shows how we want to get to milestone 3. You see on the x-axis, it's code distance. So you want to show that as you go to larger code distance, the logical error rate shown on the y-axis comes down. So the quality essentially shows quantity and quality. And quantity is how much you go to the right on the x-axis, and quality can be seen with how steep is this curve coming down. And originally we thought, oh, we have to go to pretty large code distances. Let's say d equals 15 or 17, which means, for those who don't know, it's a 15 by 15 array of physical qubits or 17 by 17 to hold the logical information. But because on the processor side, progress was faster than expected, we think that maybe a d equals 11 or a d equals 9 may be enough to reach the milestone 3. So with this, I want to go to second track, that is the software track. And quickly recap, of course, on the software side, what's really the challenge? The challenge is you want to do a beyond classical useful computation. Yeah, so where do we stand on this? So in terms of beyond classical, we introduced in 2019 this benchmark we call random circuit sampling. And ever since we did it for the first time, the cost to repeat this experiment, or if you compare, you run it on your quantum chip and you run it on a classical supercomputer. You see that the time to do it on a classical supercomputer has pretty nicely grown by a double exponential rate. So when we did it in 2024, it's now 10 septillion years that the top supercomputer would need to run this. So completely impossible, showing that quantum computing is really good at something. Of course, we were criticized often that random circuit sampling is not solving a problem that people on Main Street have. That is very true. But what's also true, if you want to buy a quantum computer and that quantum computer cannot do this benchmark well, it won't do anything practical either. So on the second, what practical or useful or interesting things can we do? So we have done a number of studies that essentially make good on Richard Feynman's dream, where you use a programmable quantum device to make an interesting quantum state, and then you study its properties. Yeah, so whether it's traversable wormholes or non-abelian anyons, time crystals, lattice gauge theories, you can already tell by the names that interesting physics can be discovered there. And indeed, we have already made discoveries. None of those would get you the Nobel Prize just yet, so we nickname them discoverinos, little discoveries. But still, each of these papers made it to high-impact journal, Nature, or Science. So the community is interested. So now the outstanding challenge that we answered a few months ago, and it graced the cover of Nature magazine, was to, I should have said this, all of these studies that I showed you there, even though they were done on a quantum processor, if you would have tried hard, you could still have done this on a big classical machine. So it was useful, but not beyond classical. And now the outstanding challenge that we answered in October was to do a computation that is both classically expensive, yet useful. And this algorithm we nicknamed Quantum Echoes. And how did this work? I want to spend a minute on explaining. So the first thing, if you want to do a classically expensive computation, how would you do it? Now, yeah, you want to run a circuit with enough qubits and enough gate operations on those qubits, and then take a measurement, measure an observable. So of course, the bigger your circuit, the more expensive this will become classically. But not so fast. You also have another challenge, because typically what your circuit is going to do, it will make a very highly entangled quantum state. And any local observable will now wash out. It will average over all the terms in the superposition. So often your signal goes down exponentially as well too, and you would have to run this many times to see anything. And then you're not necessarily winning. So how did we answer this or deal with this? By refocusing. So we do half of the circuit, implementing some unitary U, and then we refocus by doing sort of the inverse of U dagger. And then basically you come back to the start place where you began. So that's, of course, not too interesting to just implement the identity. So we need to do something more. So what you do when you're in the middle of the circuit, so now you are deep in Hilbert space, there's a huge superposition. And now you tickle one of those qubits, and we call this a butterfly operator because it's related to the theory of chaos. You do this on one qubit, on a qubit further away, we call it the probe qubit. You look how the effect of this butterfly is reaching this probe qubit. And that allows you to learn properties of U. So now the two questions: why do we think this is hard? Now, first thing you do that's maybe not too intelligent, but important to do, is we spent 10 person years to do red teaming. So 10 person years were invested in trying to run the very best classical algorithms and see how difficult this is. And we found you can't really do it very effectively. But you always cause in danger. Some smarty will come and she will show you, hey, I can do this better. So we also found an experimental protocol to check that this is hard. Because if your final observable, by the way, these observables that I just mentioned, where you go forward and backward and you check on the effect of a butterfly, this is called an out-of-time order correlator. So this is the technical term for quantum echoes. And what we did to convince the physicists that this is hard is in the middle of the circuit, we put a so-called cut, which consists of putting a gate, a dephasing gate, onto every qubit. So because dephasing, and of course what makes quantum computing expensive for classical machine is keep track of many, many paths, Feynman paths that interfere to construct the observable or the value of the observable. And if you then see you are sensitive to dephasing, that's a good indication, oh yeah, interference really plays a role here. And we could find this. And then interestingly enough, we found it for OTOC, but it wasn't quite as strong as we had hoped. So we were a bit disappointed. So then our team came up with, why don't we repeat it? We go forward, backward, and then again, forward and backward, and then repeat it. So then we found two things. A, experimentally we found the sensitivity to dephasing became much bigger. So that's a good indication. And then, don't have the time to explain this, we found if you just write down the mass, you find that, by the way, this is called OTOC square now, and you find theoretically that there's much more opportunity for long-range interference. And when we tried to publish this, Nature editors were not happy and said, oh, what the heck is this? This is not it's a weak algorithm, but it helps when you have a Nobel Prize winner on your team. So Michel Deverett said, no, this is not a bug, this is a feature. This is like going from single-pass interferometry to multi-pass interferometry. Now you're really sensitive to the properties of your unitary, and that's a good thing. So in a way, it's sort of, you can turn this into LIGO for molecules. And that brings me to the last slide here. I hopefully convinced you that it is classically hard. Now I need to convince you it's also useful. And there we have a companion paper that shows how you can use OTOC signals for quantum machine learning of molecular structure from nuclear magnetic resonance data. And that works really nicely. So there's a new protocol available now for NMR based on OTOCs. Okay, finishing my software update with this slide here. Of course, there are many other algorithms we work on, and one area that's of course quite important for quantum computing is cryptanalysis. And we have this wunderkind on our team, Greg Gidney, who likes to have the world record in such things. And he showed in a paper this year that 2048-bit RSA integers using Peter Shor's algorithm only need 1 million physical qubits to execute. And that's relevant for us because this is our milestone 6. It shows that we will end up at a cryptographically relevant machine by the end of our roadmap. But maybe also important to say, we start saying this, there's no time to procrastinate because there are other codes that are weaker. For example, Bitcoin is secured with 256 elliptic curve cryptography. That's a weaker code than this. And times are really moving inward very rapidly, and it's time to move post-quantum. Okay, so Ike encouraged me to say, I mean, it's a beautiful occasion, like starting QMIT, a new initiative. So we want to maybe lift our side a little bit and look at more audacious, thought-provoking things. And I worked in AI before, and there's a reason we called our lab at Google the Quantum AI Lab, because we believe that using quantum resources to enhance AI will lead to a more potent, powerful form of AI we like to nickname quantum AI. And things that quantum computing will do for AI, there's a long list, but maybe just consider a single example. AlphaFold, another Nobel Prize. How did it reach its marvelous success? Of course, like any AI, it had to be trained. Where did the training data come from? That was a tedious endeavor. The main database, the protein data bank, was started in 1971. So it mined, in a way, a 50-year endeavor of making good training data. And one of the first things that I believe quantum computers will do for AI is to cheaper and faster create training sets that then AI can be trained on. For example, nuclear fusion, to just get 1 second worth of data of plasma in the right conditions conducive to fusion reactions would, at current technology, cost you $1 trillion to make this data set. But in a programmable quantum computer, you might get there much quicker. But despite all its successes that AI had for, or successes in artificial intelligence, I think there are still blatant holes in understanding natural intelligence, or I should say natural sentience. Because if you work on the brain, and I have some background in neuroscience, these questions like, when I have a toothache or I smell a rose, what constitutes, what physical process implements this conscious experience? And it's often being said, if you ask this question, you better be tenured, it ruins your career. I often wonder, why is this? Because there's obviously this ontological primacy, that is undeniable. Thinking about a concept like the Big Bang is much more tenuous, whether in 100 years we will still think of the Big Bang as we do today, I don't know. But in 100 years, humans, if they're still around, will think of their toothache the very same way. And it's somehow an embarrassment that we have made so little progress in understanding what is the underlying, what process creates conscious experience, and is there such a thing as true agency or free will? And together with external colleagues, I formulated a conjecture that quantum processes need to be considered, that essentially quantum processes create a conscious experience. And in these 15 minutes, I won't have time to explain it to you. There's a paper that explains how we arrived at the conjecture. And more importantly, it explains an experimental program, how we can test it. Because once you understand what quantum process, if you're right, may constitute or implement, in modern lingo, conscious experience, then it should be possible, by linking a human brain to a quantum computer, to sculpt the conscious experience of the person linked. But now the experimentalists here, that, oh my God, when they're talking about how will you ever do this in practice? And we started baby steps to make good on this idea. And the first step we did is we apply isotopes of the noble gas xenon to different biological systems. The biological systems we choose are brain organoids, which are little lentil-sized balls of generical cortical tissue. And the experiments that I like the most, because a high schooler can repeat it, is exposing Drosophila fruit flies to xenon. So why xenon? Because xenon is an anesthetic. And you may wonder, what business does a noble gas have in being an anesthetic? And which goes to another, I think, related important question. We use anesthetics since 180 years. It's a medical godsend, yet we have no clue how it works. So what we did is you take a syringe, you put about 40 flies in there, then you keep 10% air, so they need to breathe, of course, and 90% xenon of some isotope. And then, I won't have time to show you those videos, but there's this plunger. So at 1 atmosphere of pressure, it's not quite anesthetic yet. So now you push your plunger in a little bit, you go to something like 3 atmosphere, so then the flies all fall to the ground. Glastonbury Festival effect. So now, once they lie down there, you pull out the plunger, and then it's really amazing. Within seconds, they're buzzing again. But now you can see for different isotopes, do I have to pull it out further or less far? And I'm glad Wolfgang is sitting here. When we discussed this the first time in your office, he said, like, you're not telling me that you can use Drosophila flies as isotope detectors. But yeah, now we have evidence that yes, you can use them as isotope detectors. And that, I think, is a beautiful step into, hey, quantum neuroscience should maybe be a discipline. Okay, with this, I'm done. Thank you.